but it's in a higher dimension. So this is the extra, I call it U/I. It's really just another spatial dimension, but for, as far as I've investigated so far, for the electron and for the photon, it only goes out of our 3 spatial dimensions on the order 2 to the Planck length, and it always rotates back in. Maybe a future video will go over this more. It kind of has to do with the measurement probability and uncertainty and stuff like that. The basic idea is that when we consider the probability of a light charge being seen somewhere in our 3D hyperspace, it's more like the charges themselves are rotating in this higher dimensional space, and what looks like the probability amplitude is really just the projection of the light charge onto our space, and it's highest where the light charge is going to pass through our 3D hyperspace, our 3D hypersurface. So it is a mapping, and it does show the direction of the light charges, but kind of like in a weird sort of like way. It becomes confusing because it's mathematically valid, but conceptually just a bit off. So the one thing I will say in all of this is that I think part of the problem that people have been struggling with to go deeper than, say, quantum mechanics and special relativity is that they're both correct. Like that's my one joke, that I'm like less cranky than most cranks, is because most cranks say that Einstein's wrong and quantum mechanics is wrong, and I'm just like, well, actually I'm the only one that says they're both right all the way down to the Planck length. So so my joke is I'm slightly less cranky for that reason. But yeah, no, quantum mechanics, as far as I can tell, seems to be valid all the way down to the Planck length. Same thing for special relativity. I think even most physicists think that special relativity will break down once they get to, like, 10 to the negative 16 meters, 10 to the negative 22 meters, 10 to the negative 30 meters, and I'm saying actually they're wrong. It's correct all the way down to the Planck length. I guess a simple way of saying why that would be is that quantum mechanics is basically like, assume a particle with, and in my model, particles must, as we define them as like light charges that have structure over time in our 3D hypersurface. In order for that to be true, they have to have a radius of at least the Planck length, which is why that breaks down. You can't have a particle at less than the Planck length. You can still have the light charges, they're just points. You can have an infinite number of them in a single space, kind of like the Big Bang. So, I mean, part of me was like, well, maybe there's something smaller than a light charge, but I'm like, well, if there isn't, it would be a pretty simple explanation for the Big Bang. You can have an infinite number of light charges at a single point, because they're just literally just points. But I don't know, it seems kind of obnoxious to say, oh no, this is the final step, there's nothing below this. Oh, where was I? The cat's distracting me. Hold on. Oh yeah, Planck length. So in terms of quantum mechanics, you can't have a particle when you go lower than the Planck length. And kind of the same thing for special relativity. It says, give me something with mass, and you put it in space, and the problem is you can't have a particle with mass at less than the Planck length, so it also breaks down. That's why they both break down at the Planck length, and that's why it's special. You can't have particles that have momentum or mass when you go less than the Planck length. That's why you get the Big Bang, basically. Anyway, where was I? Oh yeah, my other assumption that I assume very deeply in all of this and have little to no evidence for it whatsoever is that all the light charges that form these structures, like in our 3D hypersurface, are almost entirely like within our 3D hypersurface. Like they'll rotate outside of the Planck length and come back in, but they basically are almost flat with our 3D hypersurface. And there's like basically nothing outside of it except for maybe say the great attractor, which is far, far away. But yeah, I basically assume without any evidence, it's a really hard assumption, but I don't make a lot of evidence for it anywhere, is that there is an extra spatial dimension, but it is mostly empty. Except for, like I said, for things like the great attractor. Where was I? Cat, stop distracting me. Why do you need pets? Alright, hold on. Let's go to page 2. I thought I was already on page 2, but... Okay, here we go. Okay, now that I've gone on a massive side tangent of a rant, let's go. Okay, so here's the photon. Okay, I showed you the picture of the photon. It's just a helix. It propagates at c. In the paper I show more of this, but basically if you take the energy of the photon, and I say half here because I just did it for one of the light charges versus both of them, so that way it was only half, and then I basically just took the magnetic force, and I ignored the electric component because it cancels out over one cycle, and then I multiplied it by distance, which in this case is lambda. When you solve for that, you get C equals the angular frequency times lambda. This is different than what is typically considered, because usually it's just C equals F times lambda, but I'm saying no, there is another dimension, and it is an angular frequency. It's not just kind of like made up frequency or whatever. So yep, and then this is a side view of it, so you can see it. Like, I'm putting this picture here because it'll be more relevant when I explain other things later. But basically you have this picture where you have one light charge and it's going up with its velocity, and the other light charge is going down with its velocity, and it rotates in a circle. And then the other light charge vector are both C, and they go out in the same direction, so they propagate at exactly C. Yep, okay, so we have the structure of the photons, two light charges of opposite sign. Yep, the C vectors are aligned to move at C. The direction of the V vectors is exactly opposite. The radius is of the order of the Planck length, and the overall structure is that of a helix. And then the constrained vectors make the light charge have momentum eV over c, but not mass eV over c squared. Okay, I think I've mostly covered this and gone on a bunch of side tangents at this point, so let's just move on to the next page. Here we go. Yeah, let's do the picture. I'm gonna do this from the GitHub account actually. I think I have the results in here. I'm pulling this one up because the structure ended up being different than I initially assumed in the first paper. In the first paper, I assumed that they would it would kind of overlap, but it actually ends up just basically being a circle. So this is basically the electron or whatever, and then this is like X, Y, U. This is stationary, so Z is just 0 this whole time. Plus, it's really hard to look at 4 spatial dimensions at once. And then this is I didn't include it in here. So you'll see that it's actually not a perfect circle, but the problem is because even though I gave it like these massively like huge registers or whatever, it starts losing precision after a while. So it just at each iteration, it just loses a little bit of its precision, and then instead of being a perfect circle at the end, it's just almost a perfect circle at the end. So yeah, there was something else I wanted to show, but I'm not gonna pull it up right now. But it basically shows that even with this model, I'll go back here, it's easier to look at, but like you don't see it, but there's actually like for the U, for the single light charge, it goes up and then back down again, and that is relevant because of the way that I calculated the minimum frequency of photons required for pair production. Because even though in my original thing I thought it would be like two circles that have like an X in the middle, it actually is just a circle like this. But even though it's a circle like this, the U component for the V actually just goes up by the Planck length and back down again. So the calculation I made in the first paper for the pair production is still valid. Anyway, you can look more into that if you care. Let's see. Yeah, so that's the picture, and then the electron and the positron basically just end up being the same, except rotated backwards around the fourth spatial dimension. So that's why, like if you technically took one and put it backward in time, it would behave the same as the other one. So that's valid in this model. And then we have the mass at rest. It's just, if we look at, m equals E over c squared, and then we look at this model. You can look more in the paper, but this is basically 2 times the charge, times the electric field, times the distance divided by c squared. You solve all this out, and you basically get, I think it's the Compton radius more or less. So that's here. And then the spin ends up being something very physically tangible. It's basically just, I literally just took the equation for the angular momentum of a spinning disk, which is how you can treat this because it's like a 2D object and it literally spins like a disk. So I just did that, and then you get the correct spin, which is, you know, h bar over 2. So in this model, like, spin is a real physical, tangible characteristic of this structure. It's not some sort of like imaginary intrinsic property. It's something you can calculate very easily based on its structure. And then the effective charge, in the first paper I only looked at it for, oh dear.